All right, quiz 5 solutions. For this quiz, a little bit longer. There's 4 different problems because I wanted to give you a definite integral and an indefinite integral for integration by parts. And then for trig powers, I really wanted an even power and then one where the relevant power is odd. So I wanted to get you a little bit of practice with all that stuff. Sorry about the long quiz. At any rate, the first problem here, integration by parts. Maybe we should have the formula handy. So there it is for reference. The idea with integration by parts is you want to choose your u so that du works out nicely, informally speaking. So we've seen examples like this before. If you let u be equal to the natural log of x, well then all that's left for the dv would be x squared dx. Du would be 1 over x dx. And that 1 over x is going to combine really nicely with v, the antiderivative of x squared, which ends up being 1/3 x cubed, when we have to put those together in this new integral that we'll create. Anyways, what I'm saying is that this is equal to u times v, so natural log of x times 1/3 x cubed, minus the integral of v du, so this v times this du. The 1 over x will cancel out one of these x's in the x cubed and kind of make it x squared, and I'll pull the 1/3 out in front of the integral. And that'll leave me with this expression. Note that I need to evaluate this first term from 1 to 2, and then my integral is still a definite integral, and it goes from 1 to 2. And often I leave this off, this 1 to 2 here, and I just let this remind me. But I guess for good notation, I should be writing them in. I don't really care if you leave this off, though. And really all that's left to do now is to take the antiderivative of x squared, and since the antiderivative of x squared is 1/3 x cubed, I can take that 1/3 and this negative 1/3 and call it negative 1/9 x cubed, and that entire thing gets evaluated from 1 to 2. And that all works out because if you evaluate this from 1 to 2 and then add or subtract and evaluate this from 1 to 2, it's the same as evaluating the sum or difference all from 1 to 2 there. So if I go through and plug in 2 everywhere, I see an x. 2 cubed is 8, so I get 8/3 times the natural log of 2, minus 2 cubed again is 8, so I get 8/9. And I'll throw the unnecessary parentheses around these two terms just to help you keep track of that's what I got when I evaluated this expression at 2. And from that I want to subtract what I get when I evaluate this expression at 1. And the nice thing about when I evaluate this expression as 1 is that the natural log of 1 is just equal to 0. So 0 times whatever just equals 0. So I get 0 minus 1/9, because 1 cubed times 1/9 gives me the 1/9. And I suppose expressions are fine as your answer, but I wouldn't leave it this way. I would probably simplify a little bit and say negative 8/9 minus negative 1/9 is the same as negative 8/9 plus 1/9. So negative 8/9 plus 1/9 is negative 7/9. And so my final answer could be written this way. Maybe I'll call this good. Here's another integration by parts formula. This one's kind of annoying. I don't know, maybe this one wasn't so great. The idea here is that e to the x is not going to get any harder or simpler when you take its derivative or its antiderivative. But if we let u equal x cubed, then our du will be 3x squared. And then the next time around, we can let our u be the x squared, and our du will be 2x. And then one last time, we can let our u be equal to x. What I'm saying is multiple iterations of integration by parts will make this thing simplify pretty nicely. You probably don't even need to write out all the different parts, but I'll do it just for the sake of my solutions being easy to follow. We're going to let u equal x cubed, and then dv is equal to e to the x dx. And then I got my du would be 3x squared dx, and my v is just e to the x. And if I go plugging all those into my integration by parts formula, I get that this integral is equal to u times v, so x cubed e to the x, minus the integral of v du, which is e to the x times 3x squared, and I can pull that 3 out in front of the integral. And I get here, which is a little bit closer to the final answer than I was originally, because now my x is squared instead of my x being cubed. So I'll kind of repeat. This time I'll let my u be equal to x squared, and therefore my du is 2x dx. My dv is still e to the x dx, so therefore my v is still e to the x. And I go plugging in all the pieces. Note, parentheses, be careful there. So I get u times v, which is x squared e to the x, minus the integral of v du. Again, I have a constant at 2 this time, so I can pull that out in front of the integral. And then what I'm left with is x e to the x. And if you don't want all the parentheses, you can kind of clean up the parentheses right now if you felt like it. I don't know if it's easier to do it now or later. I'm going to do it now just so you can see an alternate way of doing things. This negative 3 hits this term and this term, so it's negative 3x squared e to the x plus 6 times this integral x e to the x dx. You don't have to do that, but now I don't have to keep track of these parentheses when I have multiple iterations of this going through. One more iteration of integration by parts. Finally, this time u is equal to x. dv is still e to the x dx. and v would therefore still be e to the x. And since u is x, my du is just 1 dx, or just dx if you want. So applying my integration by parts formula on this stuff, I get that it's u times v, so x e to the x, minus the integral of v du, so e to the x dx. And this is great, because I love to see the integral of just e to the x, because I know what that is just e to the x. So leaving this as e to the x, but not forgetting to take the 6 and distribute it to both this term and this term, I think what I get as my final answer is this mess right here. If you felt like factoring out an e to the x from all of these terms, you could do that as well. I don't really feel like it, so I'm going to leave my answer just the way it's written. All right, now we're dealing with trig powers here. These are kind of annoying, I guess, for lack of a better term. The idea on this problem is you don't know the antiderivative cosine to the 4th power of x, but you could do this little trick and say, well, I know that cosine squared x is this expression. This you get from algebraically rewriting your double angle formula. So what I can do is think about my cosine to the 4th power of x as cosine squared, because when you raise exponents to exponents, you multiply those exponents, and 2 times 2 gives me this 4. And then replace this cosine squared x right here with this entire mess. And so now I have a product of two things being squared. This 1/2 is being squared, and also 1 plus cosine of 2x is being squared. So the 1/2 squared gives me a 1/4, which is a constant, so I can pull it out in front of the integral. And that leaves me with 1 plus cosine of 2x squared, which I need to think FOIL on. Gives me 1 plus 2 cosine of 2x plus cosine squared of 2x. And unfortunately, we're not quite done. This isn't something we can take the antiderivative of. This term is, but this term's not. But this term can be dealt with pretty easily using this formula again. Instead of writing cosine squared 2x, well, if cosine squared x is 1/2 1 plus cosine of 2x, then cosine squared of 2x is 1/2 1 plus cosine of 4x. So you probably could take the antiderivative of this whole thing, but I'm going to do one more step. I'm going to take this 1/2 and distribute it into these parentheses. And then the 1/2 that I times 1 will give me a 1/2, which I'll add to this one. So that gives me 3/2 instead of 1, plus 2 cosine of 2x plus 1/2, because the 1/2 has to hit the cosine of 4x also, cosine of 4x dx. And that's just to try to make my antiderivative step a little bit easier. I think I can just take these term by term. The antiderivative of 3/2 is 3/2 x. The antiderivative of 2 cosine of 2x, well, maybe start by just leaving the 2 alone. You could do a u substitution on the 2x if you felt like it, but as we've been doing in this class, you don't really need to. You can just think about, well, let's see, the derivative of sine of 2x would almost be cosine of 2x. The problem is the derivative of sine of 2x would give me an extra 2 when I took the derivative of the 2x part. So I'm going to have to throw a 1/2 out in front here to cancel with the extra 2 I'd get here if I want the derivative of this thing to be equal to this thing. Similarly, I'll leave the 1/2 out in front as a coefficient, and then I'll be like, well, cosine of 4x, that's almost the derivative of sine of 4x, but the derivative of sine of 4x would involve an extra 4, so I'm going to need a 1/4 out in front to make sure that when I take the derivative of this thing, I get back to just the cosine of 4x. And now distributing this 1/4 and combining some fractions, I get 3/8 x plus the 2 and the 1/2 cancel, so 1/4 sine of 2x, plus 1/2 times 1/4 is 1/8, times 1/4 is 1/32 of the sine of 4x, plus c. And you're probably pretty spent at this point, but there's one more problem. The good news is it's probably the easiest of the problems on here. I don't know, it's a u substitution that works out pretty nicely. What you're going to do is you're going to save one of these cosines for an eventual u substitution where you let u equal sine of x. So you're going to change the remaining cosines into sines. And the way you do that is because sine squared plus cosine squared equals 1. That tells you that cosine squared is equal to 1 minus sine squared. So what I can do is I can replace this cosine squared with the 1 minus sine squared, and that'll make a u substitution work out really nicely. That takes me here. I'm going to let u be equal to the sine of x, and the derivative of sine of x is cosine of x, so therefore du is cosine of x dx. And all the pieces will go away ever so nicely. This cosine of x and this dx will change into du, and this will be 1 minus u squared times u squared. And if I want to figure out the antiderivative of this, all I have to do is distribute the u squared through to get u squared minus u to the 4th du, which works out really nicely with my power rule. The antiderivative of u to the 2nd power is 1/3 u to the 3rd power, and the antiderivative of u to the 4th power is 1/5 u to the 5th power. I'll tack on my plus c, and then I'll change my u's back to sine of x, and I'll be done with this quiz. So there's my final answer, and that's the quiz.